IOE 413, Mathematical Preliminaries Study Guide. This problem begins with the LP that you see here. Now, the way it's written down in the problem does not have all of the variables ordered from 1 through 4. So, for example, in the first constraint, you see x sub 1, and then x sub 4, and then 3, and then 2. The second constraint is, in fact, what you'd expect, x1, x2, x3, x4 in terms of order. And the final constraint goes x1, x3, x2, x4. So what I suggest that you do to begin with is to write this in reordered form so everything is increasing order of x1, x2, x3, and x4. So now I have rewritten the problem with the variables ordered from 1 through 4. So we have x1, x2, x3, x4, x1, x2, x3, x4, x1, x2, x3, x4. And this will facilitate turning it into the what I call pseudo-matrix form, step 1 in the 6-step process of making a dual linear program that I presented in the lecture. So let's begin with step 1. I'll write it up here just to remind us that that's what we're doing. Step 1. And that involves creating what I call the pseudo-matrix form. And we'll write it down here. Max z is equal to, and now the key part of doing the pseudo-matrix form for creating a dual is lining up all of the numbers so that we will easily be able to see what goes in what row and what column. So we'll start with the objective function coefficient vector 4153 times the column vector x. So this column vector x you can think of as having 4 components to it, x1, x2, x3, and x4. And rather than writing out all the x1, x2, x3, and x4, we'll just write it as x here to keep things a little bit simple, or at least in the objective function. And then what we do is we write down the constraint coefficient matrix 1, 5, and minus 1. And the reason we reordered our variables, so they go x1, x2, x3, x4, is so it would be very easy to create this matrix. Minus 1, 1, 2, minus 1, 3, and 3, and 3, 8, and negative 5. We'll put some brackets around this, make it a matrix. And now, what I will do is I will actually write out x1, x2, x3, and x4, because we have enough space here. I just wrote it down as an x above, but this we know is x1, x2, x3, and x4. Okay, so what we could do is we could go now at this point if we wanted to and erase this just to make it nice and simple. We're going to erase the x vector we wrote out 4 components and just write down, like with the objective function, we have an x 4-component column vector. Now the key part of the pseudo-matrix form is writing down explicitly the inequality sign here for each individual constraint. So happens in this problem that they're all less than or equal to. They don't need to be less than or equal to in general for a general problem. For this problem, they do happen to all three be less than or equal to. And then we carefully write the right-hand sides to our constraints. So they're lined up with our constraint coefficient over here. So the first constraint, the coefficients are there, and the right-hand side is right there. And the second constraint, coefficients are there, right-hand side is there. Third constraint, coefficients are there, right-hand side is there. And then also you can see that everything's lined up in terms of columns over here for our cost coefficient vector and our constraint matrix. Now, the next thing we do is we explicitly write down our, that's x sub 1, this is a comma, this is x sub 2, comma, x sub 3, comma, x sub 4, and all of these are in fact non-negative. They're greater than or equal to 0. So that's our LP in what I call pseudo-matrix form. Now the second step in the 6-step process, write it down here, step 2, is to associate dual variables with each constraint. And you know, I like dual variables that are like pi's, so pi 1, pi 2, and pi 3 are the three dual variables for this problem. One dual variable is associated with each constraint. So the first constraint is associated with pi 1, the second with pi 2, the third with pi 3. These are not multiplications here. Okay, this isn't 1 times pi 1. This is just writing down the dual variables right next to each constraint. We're going to do this so that it'll be very easy later to associate the things that need to be associated with each other in this problem to correctly create our dual formulation. So step 2 is writing down the dual variables to the right-hand side of each one of the constraints. So now let's do step 3 of our 6-step process. And this is creating the dual objective function. Since the primal is a maximization, the dual will be a minimization. It's easy to write down. Instead of z, we'll have v. And what we'll do is we'll write down our vector of dual variables, pi sub 1, pi sub 2, and pi sub 3 times our right-hand side. 1, 55, and 3, and that is just pi sub 1 plus 55 pi sub 2 plus 3 pi sub 3. And that's our dual objective function. So now let's do step 4. This step involves creating the dual constraints. And the first dual constraint comes from the information that is the primal associated with the first primal variable. So the first primal variable is x sub 1. The relevant data here that we need is the first column of the constraint matrix and the first cost coefficient. What we will do is write down a row vector of dual variables, pi sub 1, pi sub 2, pi sub 3, and then multiplied here the first column of the constraint matrix, which would be 1, 5, negative 1. So we have this 3-element row vector times a 3-element column vector. And then the right-hand side will be 4. And we get 4 from the cost coefficient. So all of the coefficients on the dual variables in the constraint come from the column associated with x sub 1 in the primal. And then the right-hand side is the cost coefficient associated with x sub 1 in the objective function. Now what we need to do is figure out whether we will plop in a greater than or equal to, less than or equal to, or equal to sign. And to do that, we will consult what I refer to as the primal dual grid. This is the primal dual grid that was in the lecture notes. And the way this works will be illustrated in this problem, that we look at the column here, whether it's a maximization or minimization problem. And of course, we're doing in the primal a maximization problem. So we start with maximization, and we need to go down the column that we just selected to look to see what the sign restriction is for the decision variable. And our decision variable, x sub 1, we just looked at, was greater than or equal to 0. So we come down this column until we look to see the variable, in this case, is greater than or equal to 0. And then what we do is we move over to the right. We see that the constraint is in the greater than or equal to the form. What it is that when we look in going from one column to the other, we're going from the primal to the dual, or the dual to the primal. So here, what we have is we have our primal, and we're moving over to the dual. So the dual will be a minimization problem. We just saw that when we created the objective function for the dual. And the constraint associated with the primal decision variable x sub 1 is going to be in the greater than or equal to form according to this table. So this means that when we are making our first dual constraint, we put in a greater than or equal to sign. So if we go back and we look at our initial statement in pseudo matrix form, what we see is that x1, x2, x3, and x4 are all greater than or equal to 0. That means that the sign restrictions will all be the same for the dual constraints. We don't need to go back and consult our table each time for each one of these. We just know that they're all going to be the same. So that means it'll be easy to write down our dual constraints. So if we go back to our pseudo matrix form that we saw earlier, notice that there's this constraint matrix that holds all the coefficients we're going to need to make our dual constraints. In order to do that, we're going to erase everything other than that matrix. So now we have just the constraint matrix. And what we're going to do is write down a row vector of pi 1, pi 2, and pi 3, and pre-multiply each one of the columns in our constraint matrix by this row vector, and then have the cost coefficient matrix over on the right hand side written as a row vector for 1, 5, and 3. And I told you that our first dual constraint was going to be this pi row vector times the first column of the constraint matrix was greater than or equal to 4. And that's still true. This is just a matrix representation of that. It's also true that pi 1, pi 2, pi 3 times the second column of our constraint matrix is going to be greater than or equal to 1. And this row vector of dual variables times the third column of the constraint matrix will be greater than or equal to 5. And the row vector of dual variables times the fourth column of the constraint matrix will be greater than or equal to 3. And the reason they're all greater than or equal to is because of what I just told you in the last slide, is that the direction of the inequalities are all the same because the sign restrictions on all the primal variables are the same, greater than or equal to 0 in a maximization problem. So this is a parsimonious way of representing the 4 dual constraints. The form that we just wrote down is perfectly fine mathematically. However, it might be a little bit more convenient if we transpose both sides. So if we transpose the constraint matrix, we will get 1, negative 1, negative 1, 3, and then 5, 1, 3, 8, negative 1, 2, 3, negative 5, and then we can write down our pi vector greater than or equal to, and transpose our right hand side so the row vector becomes a column vector. So it's 4, 1, 5, 3. This is just exactly equivalent to what we saw on the previous screen. The only difference is that I transposed both sides, and instead of writing down pi 1, pi 2, pi 3, I wrote down pi as a pi vector. So on this screen, this represents a column vector of pi 1, pi 2, pi 3. Now we can do step 5. And step 5 involves determining the sign restrictions on the 3 dual variables. So let's consider the sign restriction on the first dual variable. It will be determined by whether it's a maximization or minimization problem and the direction of the inequality in the first primal constraint. So let's go to our primal dual table and determine the sign restriction on pi sub 1. So we have a maximization problem. We're looking at constraints now, and we see that the constraint that we're concerned about, the first constraint, the primal, is less than or equal to form. We come down there, go over to the right to see what the corresponding sign restriction on the dual variable will be, and we get greater than or equal to 0. So the sign restriction on pi 1 is greater than or equal to 0. But notice that was driven by the fact that there was an inequality less than or equal to in the corresponding primal constraint, and the primal problem is a maximization problem. But the same thing is true for the second and the third constraints that are related to these second and third dual variables, respectively. So that means they all have the same pattern. They're all greater than or equal to 0. Pi 2 and pi 3 are also greater than or equal to 0. So those are the sign restrictions for this problem on the dual variables. So now we can write down the full dual problem. We have all the pieces in place. Earlier we determined that the dual objective function was 1, 55, and 3 as a row vector times pi. Pi here is a 3-element column vector, and also pi is greater than or equal to 0. So that's the dual LP. So finally we're on to step 6. Step 6 is just checking some simple things at the end to make sure that we did the problem right. So the first thing you can do to check is to make sure that if your primal was a max, the dual is a min. Or if the primal is a min, the dual is a max. Max goes to min goes to max. So we started out with a max, and we have a min, so check. That makes sense. We've done that right. The other thing to check is that we do not have any primal variables, no x's, in our dual solution. Seems obvious, But many times on exams, students end up having a dual that has the primal variables left in it for some reason. And that's kind of a shame because it's a very easy thing to check. At the end of making a dual, you can go back and check to make sure if you have any primal variables in there. If you do, you did something wrong and you need to go back and check. So let's look here in our problem. Well, we have pi's, we have constants here in our coefficient matrix, our right-hand side. We don't have any x's. So check, we did that right. And finally, the third thing that you can do is to make the dual of the dual, and that should be the primal. Now that takes a lot of time, and I'm not going to do it here, but if you have time at the end of an exam and you have plenty of time and you're wondering what to do, don't just turn your exam in. Go back to the problems where I asked you to make a dual of a problem, and then make the dual of the dual and make sure it comes out to be the primal.